I'm gonna talk about the conical pendulum again briefly. I actually have the quest assignment in front of me. I'm gonna go over some points for every example that you'll see on the quest assignment that's gonna deal with centripetal motion.
A new one?
Yeah, it's a new one. Yeah. So those of wrong way.
Do we have any other daily grades besides quest?
No, not really.
Cool, yeah.
Okay, so conical pendulum. Yeah. Conical pendulum. The view's a little skewed on the video, but deal with it. Okay. So obviously the pig's moving in a circle. The wings are not providing any lift. The wings are there to just counteract the air resistance that would cause the pig to slow down, which then would reduce the centripetal force for reasons that we'll talk about in a second. But the pig is moving in a horizontal circle at constant speed, and the circle has constant radius. Okay, and so I'm going to stop that so that if there's time at the end, you can play with the piggy. His name is Wilbur.
Like Charlotte Swift.
Yeah.
So he dies at the end.
That is why.
Thanks for the spoiler alert. I'm reading that right now, Bradley. Okay, so
I'm making up my second grade reading.
so the conical pendulum. Here's the pig. He's going to be moving. Obviously, it's three-dimensional because cones are three-dimensional objects. He's going to move out of the board and then back into the board. So we'll assume I'll draw his velocity vector in green. Velocity vector at this point would be coming out of the board, and then over here it would be going back into the board. So that's how we draw three-dimensional now, since we're doing 3 dimensions. The string, if I drew that well, would go to right about there. And then I can label the radius. And I'll actually show you later today with a gravity simulation or I'll get to that. So there's the radius of the circle, or why the, never mind. So if I want to analyze the forces on this, obviously the pig's moving in a circle because it's experiencing forces, non-zero net forces. This is something that's hard for a lot of students, and we talked about this last year pretty extensively. Hard for a lot of students to understand. If an object is turning, it is accelerating, regardless if its speed is changing or not. If the velocity is changing, that means either the speed is changing or the direction of the velocity is changing. Either of those is an acceleration, or both of them together is an acceleration. So even if you're going constant speed, which the pig is, it is constantly accelerating, which means it has a constant non-zero net force, which we can see by just doing the free body diagram. Free body diagram for the piggy, for Wilbur, has a tension force pointing up this way, and then a weight force pointing down. And yes, there's the drag force, but then there's also the thrust force that the wings are propelling it forward with, and those balance out, so we're not going to consider those. You add these two vectors together, and they don't cancel each other out. They don't balance each other out, right? If I decompose my tension force, then it becomes obvious. This is Ft. I'll say this angle right here is known. Very often we're given the angle of the vertical, but then you can just use your knowledge that these two angles have to be complementary. So this would be Ft cosine theta. The vertical one will be Ft sine theta. And obviously, the pig is not accelerating in the vertical direction, so mg must be balanced by Ft sine theta. So you can write that as an equation. You can say Ft sine theta equals mg. So you can actually calculate the tension if you know the mass of the pig and you know the angle. You can measure the angle. Sometimes they don't give you the angle. Sometimes they give you the dimensions of the conical pendulum, and then you have to use inverse trig functions to determine the angle. And this is, again, net force equals, and this is in the y direction, equals mass times acceleration. Acceleration is 0. Net force is 0, which leads to this statement here. In the x direction, though, there's only one force, and it is not 0. Therefore, it's accelerating, right? Necessarily. If this force doesn't have another force balancing it, the object must necessarily be moving. But because it's moving tangentially to that force, it moves in the circle. Right? So there we can say that the net force in the x direction is mass times acceleration in the x direction. The net force is just the single force, tension times cosine theta. And that's going to be mass times the acceleration in the x direction is actually a centripetal acceleration. And we proved the other day that the centripetal acceleration is simply v squared over the radius. So if I wanted to take this out even more, I could say ft cosine theta equals m v squared over r. And I can even dig more into it, because I know the distance that the pig travels as it goes around the circle is 2 pi times the radius, right? So I can say, well, v, the linear speed, notice I'm saying speed, not velocity, because the direction is constantly changing, but we're assuming constant speed. That v is distance over time, or 2 pi r, the circumference divided by the time it takes to go around one time, which, as we saw yesterday, is called the period, the time for one complete revolution. So you can always plug that in for v here and expand that out even more. It's good times. So I'm not going to show an example problem with this, just understand. I want to get to more interesting example problems, but understand that you can always get these equations for a conical pendulum.
So wouldn't be accelerating in the z direction either, right?
No.
Okay.
No. Oh, yeah. The acceleration is constantly pointing towards the center of the circle. Centripetal literally comes from the Latin root words for center and seeking. Center seeking. So when you do centripetal motion, don't be thinking x, y, z axes. Think the axis that's perpendicular to the circle, and then just call towards the center of the circle the positive direction.
Okay.
No matter where it is, because it's always going to be the same. But it's actually technically constantly changing direction as well. The acceleration is. But if it's constant magnitude, then just call towards the center of the circle the positive direction. Center seeking, remember center seeking? Well, seeking the center is the positive direction regardless of where you go. And that's fine. That's fine for our purposes. Cool beans? All right.
Frioles calientes.
All right. So I want to talk about gravity a little bit now.
The not real force.
What's that?
The not real force.
The not real force, yes. But for us, it's a real force.
Oh, okay.
For practical purposes, you can assume it's a force. It's only when you get into the realm of extremely high speeds and very strong gravitational fields. It's fine. It's fine. So here I got a planet orbiting a star. Good, big enough. Okay.
Or is it?
Or is it? Or is it moving in a straight line through four-dimensional space-time?
Or is the sun orbiting the planet?
Oh, yeah.
From the perspective.
Now I did specifically make the sun way more massive, so it's pretty. No, actually, I put a pin in it and actually stuck it there, so it's not moving at all. So another way of seeing, where's my mouse? Another way of, I can't think and do at the same time. Another way of seeing the direction of the centripetal force, that is not going to work. Is by looking at it geometrically. Because we know that the acceleration, the definition of acceleration is change in velocity over time. Right? That's a definition of acceleration. And it is a vector, and it points in the direction of the velocity change vector. Right? The change in velocity vector, which is a thing. And I know that the change in velocity vector is final velocity minus initial velocity. Well, let's just pick two random velocities here. Let's call this our initial velocity vector. V naught, initial velocity vector. And let it go So right there, call this our final velocity vector. Now, if I wanted to say the average velocity, you guys know that if you find the average velocity, if you're moving in a straight line, you just add them together and divide by 2, right? If I wanted to talk about the object's average velocity as it goes from here to here, wouldn't I draw that vector from right in the middle? Wouldn't that make sense? Like if I backed up a little bit. Between these two vectors, I would say, their average velocity is pretty much right about there, right in the center, right?
Yeah.
Can we kind of understand that? Okay. Now remember that when we subtract vectors, final velocity minus initial velocity is the same thing as final velocity plus the negative of my initial velocity, which means my initial velocity, just flip it and then add them together normally. So my initial velocity vector points this way. Its negative would be this vector. If I add this vector to this one, right, final minus initial, then I would take this and move it down to here. Well, something like that. Wait a minute. Yeah. I didn't, sorry. Oh, it's good, right?
Yes.
There you go. So there's negative V naught. And the resultant points in this direction right here. So that's the vector that represents my change in velocity. Now remember, I would draw that, and it has the same direction as the acceleration, right, by this equation here. So if I were to take that vector and put it where the average velocity between those two times was, I'd put it here, and it would literally, if I had done this well, it would literally point towards the center of the circle, and that would be the direction of the centripetal acceleration. Does that make sense? The closer you get these two, obviously, the closer you get V and V naught, the easier it is to draw it by hand because it would be a very small change, but that's when you start using calculus, and we don't know calculus, so.
Yeah.
So that's why it points towards the center. Okay. Some interesting, so there's a geometric demonstration of why it points towards the center, but the rigorous one we did the other day, the rigorous demonstration. Now what's interesting is that this guy, this planet, has a certain mass and is traveling at a certain speed. Anyone remember last year? What if I changed the mass of this guy, but I still want him to be in orbit? What else would I have to change? I have to change the speed. We'll see if that's true. I don't know. Maybe it is. So let's see. Let's go ahead and talk about the gravitational force, which is causing centripetal motion. So I'm going to apply Newton's second law here. I'm going to say that the net centripetal force is mass times centripetal acceleration. If you get a problem with circular motion on a FRQ on the AP exam, never label a force on your diagram, free body diagram, as a centripetal force. Any force can be centripetal. Tension, gravity, whatever. Whenever you draw your free body diagram, like I did with the conical pendulum, I didn't put centripetal force. I put tension times the cosine of the angle. Right? So always label it with the actual force that's causing the centripetal motion. So net centripetal force here, I only have one force.
Wait, so why did you label it centripetal force?
Just the statement of Newton's second law for centripetal motion. But then when I go to the next step, I'm going to identify, because sometimes there's more than one, right?
Okay.
Sometimes there's more than one. Sometimes you have a force that points towards the center, one that doesn't, in which case I wouldn't write net centripetal force, I would just write net force, right? But here I'm just reminding myself, this force is going to cause centripetal acceleration, so the net centripetal force equals mass times centripetal acceleration. Notice this is a vector equation. Another demonstration of why the acceleration has to point towards the center of the circle, because the gravitational force does too. So in the next step, I do say force of gravity equals, and here too, this is my free body diagram essentially, right? I just put FG. This is going to be the object's mass, the object that's moving in the circle, times its speed squared over r, right? Do we have another expression for that gravitational force?
Yeah.
I'll say m star times the mass, which is just the mass of the planet, divided by the distance squared. What happens?
On the formula sheet?
What?
That is on the formula sheet.
This?
Yeah.
Oh yeah, this is.
So planet's mass doesn't matter then?
Planet's mass doesn't matter. Everyone brought mass to the party. Trent, you fail for today. I'm just kidding.
Can you also get rid of one of the radiuses?
Yeah. One of the what?
Radiuses.
One of the radii?
Yeah. You know.
Yeah.
I think they do.
I say radiuses too. I like momentums too. Momenta is the real word, but I don't like that one. So yeah, in the next step I get v squared equals g mass of the star divided by r. I can just square root both sides. Now, what assumption went into this? The object is moving in a circle, a perfect circle, uniform circular motion. So this is the equation for a circular orbit. If you know the mass of the object, and you know the distance that you want to put a satellite, and you want it to be in a circular orbit, that's the speed it's got to be by the time it gets to that distance. Right?
What about
Then it gets more complicated. And we're not really going to talk about the math of that too much in this class. We talked about cones at the beginning. You guys know what a conic section is?
It's a parabola.
Hey, the parabola is a conic section, but so is a point, so is a line, so is an ellipse, so is a circle, so is a hyperbola. Oh, it's beautiful stuff. Beautiful stuff. So when you learn about that eventually, it's good stuff. Yeah, you cut a cone through the center, or you just cut a cone across. If it's like standing upright and you cut it across, you get a circle. If you tip it a little bit, you get an oval. You get an ellipse, right? If you have two cones that are tip to tip and you put it right through, there's the point, right? You can line up on the edges of the cones, the two cones, and just touch it at a single line, so it could be a line. It's good stuff. It's good stuff. Anyway, so this is not on the formula sheet, but sometimes you can always derive it using Newton's second law for centripetal motion and equating it with Newton's law of universal gravitation. So you'll definitely do that on the quest assignment for tonight. Speaking of, let's talk about ovals a little bit. Let me turn these guys off. Actually, no, not the velocity. The values. Turn the force off. Okay. So let's look at this guy's speed here. And I'm going to reduce the speed a little bit. It's at 0.6 meters per second. Let me go down to 0.4 meters per second. What do you think will happen if I go slower?
Object will move slower.
Wrong. No, I'm just kidding. What do you think is going to happen to the shape of its path? Is it going to fall into the sun?
It's going to move closer to the sun because the radius has to compensate for the lack of speed.
Yeah, kind of. But it doesn't necessarily have to fall into the sun. Now it's going to have an elliptical orbit.
Wow.
And that ellipse is going to be inside of the original circle.
Now we have a name.
What's that? What's the original speed again? 0.6? What if I go faster?
3.2.
Then it's going to be
What do you think? Yeah.
yeah, it's going to zero the ellipse.
It's going to be an elliptical orbit, but the circle, the original circular orbit, will be inside of it. So this speed, if you go faster than it, you'll be in an elliptical orbit that will be larger than the circle. The circle will be inscribed within it. If you go slower than that, then you'll be inside the circle.
That's crazy that
But if you go
that
too-
small the changes.
But if you go too fast, it will.
But if you go too fast,
Shoot off, right?
reaching what we call escape velocity, which we'll talk about at the end of mechanics.
Make the velocity 3.2.
3.2? Now that's not a straight line. Let's actually do a not quite that fast. Let's go to like 1. Let's speed it up. You might still be in an elliptical orbit. We'll have to see. Doesn't look like it. Look like he's got escape velocity. That is a hyperbola.
I was gonna say it's a row.
That's a conic section. Isn't that weird? Motion. It's all about, you can describe all motion in conic sections. Yeah, this is a hyperbola. You know those graphs that look like this? Not inverse graph. Okay, I don't want to get too much of that. Yeah, kind of. How about like where you have asymptotes right here? Those graphs. Yeah, it's good stuff. So you don't need to know how to calculate those orbits, but it is in the standards that circular orbits, you need to be able to calculate that to determine that and then do stuff with that. But you also should know that if you go faster than that, then you'll be in an elliptical orbit with the circle inside of it. If you go slower than that, you'll be in an elliptical orbit with the circle outside of it. Note, and this is interesting.
So basically, if your satellite's barely off on speed, you're screwed, right?
Yeah, that's why they calculate stuff ahead of time and they plan. A lot of pre-planning, you know. It's pretty interesting though, because if you're in a spaceship and let's say that you got a baseball in your hand and you're on the outside of the spaceship and you're in orbit and you're looking down at the Earth and it's right there and you want to throw that baseball down to your friend that's on the Earth and have him catch it, it ain't gonna happen. It ain't gonna happen because you're moving this way at 18,000 miles an hour and you give it a little dinky velocity this way, well, you're just going to cause the motion of the baseball to be slightly, it's actually going to end up going higher than you on this side, and it's just going to be an elliptical orbit that's slightly more eccentric than the one that you're in. So it's literally impossible unless you're like, unless you're Mr. Henderson. You can't get it there. You can't get the ball. You throw as hard as you want. As hard as you want, it's not going to get. It's not going to get to the Earth.
Really hard.
Yeah, well, there is a speed at which, yes, you could do it, but no human is capable. Yeah.
Wait, okay.
We're still recording. Okay.
So, if you like shot like a bullet at the Earth, would the bullet be able to go fast enough, or would that still not be?
I don't know how fast do bullets go.
Very fast. That's a good question.
Well, yeah, but not as fast as satellites.
Faster than bullet.
Does the fastest?
Not as fast as Superman.
2,600 feet per second. So that's
How many miles per hour is that?
1,800 miles per hour.
How many meters per second is that?
That would be like, I don't know,
That's a lot.
at least 3.
Okay, let's talk about circular motion now. Now I'm going to turn gravity off. We talked about this at the end of class yesterday. Let me turn that force vector down a little bit. So without gravity, it's just uniform circular motion, right? Because gravity's not speeding it up on the way down or anything. It's not perfect, but yeah, it's a little bouncy. That's because there's some bounciness in the string. Okay, so this is uniform circular motion. But if I why are the forces so big? If I turn gravity on, wait, that's not with gravity on. Oh my gosh.
Mr. Graham.
Oh my gosh.
Oh, Mr. Graham.
There we go. This is what we were talking about yesterday. So, very different motion when we have vertical circular motion. Technically, this isn't uniformly accelerated motion or uniform circular motion because it's not traveling at constant speed, although it's still traveling in a circle. Notice that C, for some reason they call C the tension force. It's at a minimum at the top, maximum at the bottom. If you ever spin something around on a string, you know that. It feels heavier at the bottom because the tension's bigger than it does at the top. In this class, and back in AP Physics 1, the only 2 times that we analyze vertical circles mathematically is when they're at the very bottom, which I missed. Let's do the top first. Is when they're at the very top. Because at the very top, it is moving in a circle. It is accelerating towards the center of the circle. But as soon as it bypasses that, it now has a tension pointing this way and a gravity pointing down this way, and so it gets a lot more complicated. But at the very top, we can say that there's a tension force pointing down and a weight force pointing down. And we can use Newton's second law for centripetal motion to analyze this motion. We can say at that point, it's going to change immediately after, but at that point, we can say that the net force, the net centripetal force, is mass times centripetal acceleration. Now I have two forces that are combining to make that centripetal force, which is the tension force at that point and mg. And I add them together because, again, pointing towards the center of the circle, just call that positive. It'll make your life easier. And that's going to equal mv squared over r. All right? And so the tension then, and again, if you're spinning this, if I'm doing this, if I'm spinning this guy around on the end of a string, right, the tension is what I feel. The tension is pulling down on the ball, but up on my hand at the top. At the bottom, the tension is pulling up on the ball, but down on my hand. So my sensation, what I feel, is the tension. And so here the tension is going to be equal to the quantity mv squared over r minus the weight of the ball on the end of the string, right? Now let's let it go around to the bottom. See right there, the net force is a lot more complicated because you got this vector added with that vector. It's no longer centripetal force now, totally. Right. But at the bottom, while they don't point in the same direction, oh dang it, they don't point in the same direction. Oh, come on.
That's good.
Is that good enough?
Good enough.
That's good enough. They don't point in the same direction. They are along the axis connecting the ball with the center, right? And so I can deal with it here, and I would do the same thing. Free body diagram. So this over here is at the top. This over here is at the bottom. Free body diagram. Actually, let me draw it down here a little bit. I got the weight force pointing down, mg, which is the same as this one, right? That didn't change. But now I have a tension force that must be pointing up. It must be pointing up, and it must be larger than mg because what's the direction of the acceleration? Up, towards the center of the circle, right? And so if it's accelerating towards the center of the circle, this force must overcompensate that force. And then I can apply Newton's second law. In this situation, net centripetal force, mass times centripetal acceleration. Net centripetal force is going to be, remember, towards the center of the circle is the positive one. So the tension force minus mg in this case equals mv squared over r. And then I add mg to both sides. So the tension that I'm going to feel is going to be mv squared over r, that quantity, in addition to the weight of the object. So not only is it larger because I'm adding the weight of the object to the equation, but v itself is bigger at the bottom. Because on the way down, it was speeding up. On the way down, it was speeding up, so the speed increased. So mv squared over r becomes larger, and then I'm adding mg here instead of here. And that's why you feel a significant difference. There's a significant difference. Unless you're spinning it real fast. There's a significant difference between what I feel at the bottom here and what you feel at the top. Right? Even if you're spinning it fast, you're still going to feel a difference.
And that's why when you're going at minimum speed, net force equals 0. Because
Net force won't equal 0. The minimum speed to get through the top. So let me show you what it looks like. The minimum speed to get through the circle. So if I'm at the minimum, right now I'm not at the minimum speed, just get through just fine. But when I start getting towards the minimum speed, oh, that was less than the minimum speed, right? It has to have some minimum speed at the top in order to keep moving, right? If it doesn't have that minimum speed at the top, then right before it gets to the top, it goes slack and it starts falling like a projectile. If it doesn't have anywhere close to that speed that it needs at the top, then it goes slack before it gets there. So that's like that, right? So there has to be some minimum speed that it must have at the very top of its motion If it has more than that, then sure, it's going to go through just fine. But if it has exactly that speed, that's where it just barely makes it through. And if it has less than that speed, or if it's going to have less than that speed, then it doesn't even get there. Okay. So how do I deal with that? We talked about it a little bit yesterday. This free body, and it's at the top. The bottom doesn't matter. It's going to get through. It's going to swing back and forth if it doesn't have enough energy to get up to the top. But what happens to our free body diagram whenever we're talking about the minimum speed? At the minimum speed, what happens at the very top? The tension goes slack at that instant, right? But then it moves a little more, and the cord starts pulling on it down this way towards the center of the circle to get it moving in the circle, and it re-engages, right? But it disengages for that instant at the very top at the minimum speed. At the minimum speed, the tension equals 0 at the top, at the very top. And in that case, net force, centripetal force is mass times centripetal acceleration. Net force here, the tension will become 0 at the very top. The net centripetal force is simply the weight force of the object. It's going to be mg. And that's going to be mv squared over r. Someone, yeah, they both brought mass to the party. They cancel. And so if I solve this for v, what do I get? Square root of rg. Some students memorize that, but it's not that hard to derive it if you need to. Make sense? Check this out. Any skateboarders in here?
Oh, is this the video?
Okay. You're so humble about it too. That's what I like about you.
You're such a modest guy.
Yeah, such a modest guy. So, well, I'm a skateboarder, and I've done the loop-the-loop many times on a skateboard.
Yeah.
Want to show us?
Maybe. I don't have time today. But so here I got an object that's sliding. I turned all the friction off. He's going to slide this way. And again, like the string, there's going to be some bounciness with the normal force here. But I got the weight force and the normal force that cancel each other out. And so it's the net force is 0 until it gets to the part in the circle right here where it's going to start actually accelerating towards the center of the circle, at which point you'll see the normal force jump up. Because it's going to have to point, the net force is going to have to point towards the center of the circle. Right? And it spikes, again it spikes, and then gets smaller as it gets to the top, and then gets bigger as it goes back down. Right? So, same situation, only at the bottom I have an upward force and a downward force. The upward force must be significantly larger, but it's not tension here, it is the normal force. And then at the top, same thing, downward weight force, downward normal force. Right? Normal forces don't have to always point up or perpendicular to a ramp. They can be down. If I get a book, clipboard. Take my remote here and I push it up on the clipboard. I'm pushing up on it, but it's not accelerating up because there's a normal force that's pushing down on it because it's just in contact with it. Right? So, but what if I want the minimum speed to get through the loop? Because if you don't go fast enough, and I think Bradley remembered it, and if I had thought about it, I would have pulled it up. But there's a video that I show my AP Physics 1 students that shows skateboarders trying to go through the loop, and their first few times when they first try it, they have mattresses that they like throw under them, like when they go up, just because they know they're probably going to fall. You got to have enough speed. If you don't have enough speed, this happens. Oh, this is way too less. Wait, no. That happens, right?
There's like one guy who
Yeah, most of it you gotta commit. Most of it people freak out, and so they end up just bailing, you know. And you gotta. It's tough. It's tough. Let me tell you, I've done it a million times. So yeah, you have to have that. So there is a minimum speed that you need to have at the top, right? So if I wanted to do that problem, the minimum speed that the skateboarder needs to have to get through the top, then I would say the net centripetal force, mass times centripetal acceleration, and here I'm talking about the top. Well, the free body diagram that I should have drawn before I applied Newton's second law says that at the top I have a normal force and I have a weight force. What happens at the minimum speed to get through the top of the loop? At the top.
0 normal force.
The normal force goes to 0. Can anyone tell me what the speed will be whenever I solve this equation?
R times G.
Square root of RG. Won't it be exactly like this?
Yeah.
The net centripetal force at the top, at the minimum speed, it's just mg. So you end up with the same exact result. So the minimum speed to get through any vertical circle is always the square root of RG. Now some students in physics C, because in physics 1 they haven't done energy yet, but some students fall into this trap. All right, well, this is the highest point in the loop, so I just need to make sure that I'm at the same height here. Because conservation of energy says that, if I start here, I have enough potential energy to get through up here. What's the error in that reasoning?
Because I'm worried.
Right, oh, good, very good.
That's where it'll get to 0 velocity, so we need to change the minimum velocity.
What's that?
That's where it will get to 0 velocity.
That's where it would get to 0 velocity by the time it gets to the top, but that means it would just magically stop here, right, and then fall, which doesn't happen. And you're this roundabout way of stating, yeah, if I have just potential energy here I have potential and kinetic energy, right? So I need to have enough gravitational potential energy so that here I have the same amount of energy, but it's both kinetic and potential, right? And as we'll learn next week, it also has another kind of kinetic energy. Spinny kinetic energy. Spinergy.
Spinach.
No, it's rotational kinetic energy, right? So it takes you have to be significantly higher to get through a loop. Okay. All right, and we have a couple more minutes. Let's talk about the vomit comet.
The what?
The vomit comet.
Oh.
Has anyone ever seen? It's kind of an old movie now, but it still holds up and it's still amazing. Apollo 13. Has anyone ever seen Apollo 13?
Yes.
It's a great movie. That's your homework for tonight. In addition to your quest assignment, you need to watch Apollo 13.
I watched it in my 8th grade science.
Good.
Oh, yeah.
Just quick question about the quest assignment. I'm just wondering why it's at the bottom of the page instead of at the top.
Oh, is it?
Yeah.
Oh, I need to move it to the top.
Okay.
My bad.
It's due November 16th at 11:59.
It's due Monday. We're gonna work on it tomorrow.
Okay.
It's due Monday night, but we're gonna be moving on Monday. Okay, the vomit comet. If you ever watched Apollo 13, you know it's made in like the early 90s, so CG was terrible. CG wasn't good until Jurassic Park, and even to this day, most movies CG aren't as good as it was during Jurassic Park. But it's another movie you need. Add that to your homework list too. You need to watch Jurassic Park too. But Apollo 13, it looks like the special effects were amazing because they're literally in the spaceship going to the moon. It's the one where all the problems happen. Excellent, amazing story that they actually got back alive. It's amazing. It's an amazing story, regardless of whether there was a movie made about it. But when you watch it, they look like astronauts that are in space. They're floating around, right? They're floating around, and it doesn't look like there's any strange or anything. The movements look like they would be if you were weightless quotes, right? Apparent weightless, and it's because they literally were, right? They didn't have to go out into space though. All they had to do is take several hundred rides on the vomit comet, and just shoot each day. I think you get like 30 seconds of weightlessness at a time. And so what the vomit comet does, it's a plane that just flies in a big circular arc. And they fly that way such that whenever you get to the top here, the normal force on you is 0. right? You know how an elevator goes up when it starts slowing down, you feel like you start coming up off the floor? Or if you go over a hill on a roller coaster, you feel like you kind of come up out of your seat, right? This is essentially that on steroids, right? It flies in a circular arc at just such a speed that normally you would have a normal force pointing up and a weight force pointing down. And if you're flying in a circular arc, mg is going to be larger than the normal force. Why is that? Because mg points down. It has to be, right? If a plane is flying in a circular arc like this, mg doesn't change. If that person is moving in a circle, that means the normal force must necessarily go down. Well, if they fly in such an arc in such a way at such a speed, the normal force goes down and goes down and goes down and becomes zero. Once that normal force becomes zero, you literally float off of the floor. Okay? And you feel like you're in free fall and you get that queasy feeling in your stomach that you get when you go over a hill on a roller coaster. But that's literally what happens. And if you go faster than that, or you have a sharper arc, then when it happens just at the top, then it starts to happen over here. And then you're weightless when it goes through a big arc and they get like 30 seconds at a time. So when you watch Apollo 13 tonight as your homework assignment, just know that whenever they're in space and they're floating around, that's when they're filming it. They're filming those scenes on the vomit comet. You can get a ride on that. It's only a few grand. Right? You can, I think.
Only a few grand.
It's only a few grand.
Shut change.
You guys got a few grand laying around, don't you? Yeah.
Everyone does.
Now what's cool.
That's my minimum bet at Windstar.
You're not old enough.
My fake ID doesn't say that.
Whoa. I don't want to hear about this. So, I'll end on this, since we're talking about the vomit comet. This is how I used to think, because I was a stupid kid. I used to think my dad would tell me, the tallest mountain in the world, Mount Everest. Tallest mountain in the world. Way taller than all the other ones. I used to picture the Earth like this and then Mount Everest being like this giant mountain from space with it sticking out like that.
Mount Everest is not the tallest mountain in the Earth. It's the
It has the highest elevation.
the highest mountain.
Yeah. So, isn't it one of the Hawaiian islands or something?
Yeah, there's something in the ocean. I don't remember what.
So, Newton's thought experiment, because he obviously couldn't do this at the time, he thought about one of the many things he did. He thought about a mountain, an impossibly tall mountain that rose out of the Earth's atmosphere that could fire a cannonball at any speed he wanted. An arbitrarily large speed, right? So if you shoot a cannonball out with not that much speed, it follows this path. And it hits the ground. Right? Because it's horizontal speed. It's fired out with a horizontal speed v naught. And then gravity engages and it falls towards the center of the Earth, right? Because the force is going to be pulling it towards the center of the Earth. Well, let's shoot it a little faster. Notice when you shoot it faster, it actually ends up covering more distance than it would otherwise over flat ground, because if it was flat ground, then it would have hit the ground right here. But no, it's going to go farther because it's actually following the curvature of the Earth a little bit.
I just
Okay? If you subscribe to the flat Earth theory, then just ignore this part of today. And fire it a little faster, it's going to follow that curvature around a lot more. Look, it might even get to the other side of the planet before it hits the ground. If you fire it fast enough, then literally the rate that it's falling towards the center of the Earth is exactly compensated by the rate at which the surface of the Earth is curving away underneath it. And so even though you're technically falling the entire time, you never reach the center of the Earth. Remember that, like it says, when it's right here, it's got the weight force, points towards the center of the Earth. That's the net centripetal force too, right? That's the net centripetal force, which is pointing towards the center of the Earth. The acceleration is towards the center of the Earth. But because it's moving perpendicular to that centripetal acceleration so fast, the rate at which it's falling is exactly compensated by the rate at which the Earth curves away underneath it, and you're then in orbit, right? And Newton figured that out. He couldn't obviously test it because they didn't have the technology at the time, but that's orbit. And this is one of the things that Newton was like, falling stuff, orbiting stuff, same thing. Same force is causing both of those. Just in this case, the force is perpendicular to very high velocities. So free fall. It's in free fall the whole time. That's why when you see astronauts in the spaceships, footage of them, they are in free fall. They're literally feeling like you would feel if you were standing in an elevator and someone cut the elevator cord and you just start falling. That's how they feel the entire time they're in orbit. And what do most people say when you say, why do astronauts float when they're in space? What do most people say?
They say it's because there's no gravity.
They say there's no gravity, right? No gravity. And that's silly because if this was the Earth, typical low Earth orbit is like this high off the Earth. It's actually pretty close to the surface in the grand scheme of things. Because the atmosphere is very thin in comparison to the diameter radius of the Earth. So to think that there's no... yeah, it's going to hit the mountain. To think that there's no gravity here, though, is silly. It's silly. There's gravity there. Low Earth orbit, it's like 8.9 or something like that. It's pretty... It's not real close, but it's pretty close to 9.8. It's pretty close to what it is on the surface. And there's definitely gravity there. There's gravity everywhere. Gravity everywhere.
The fake force.